says. It's my pleasure now to start off our afternoon session by introducing Dr. Noriko Hayakawa, who's head of the Restoration Materials section at the Tokyo National Research Institute for Cultural Properties, the Tokyo Kokuritsu Bunkazai Kenkyujo. And Dr. Hayakawa has really published widely on the use of traditional organic materials in the conservation of art. She's also the editor-in-chief of the Journal of the Japan Society for the Conservation of Cultural Property. And I should just say that really the leading scholar in Japan right now of translating into the language of science the workings of traditional Japanese materials in art conservation. So please join me in welcoming Dr. Hayakawa.
Thank you. Hello. My name is Noriko Hayakawa, and thank you for inviting me to speak to you. And I'd like to mention to many thanks to organizer and Dr. Yukio Lipid for supporting us. Thank you. Oh. I'm a conservation scientist in Japan who focuses on the research of organic conservation materials. Can you listen? Okay. As many of you know well, East Asian painting materials are different from those in Western paintings. They are composed primarily of fragile materials such as silk, plant fiber, and animal glue. I study these traditional materials and how they are used in order to better enable the conservation of Japanese paintings. In particular, I research traditional Japanese materials used in art and art conservation from a scientific point of view, thereby attempting to better understand their properties and methods of use that are otherwise poorly understood. In this presentation, I'd like to introduce select examples of my research concerning such materials and methods, and their implications for how we understand the conservation of traditional Japanese painting. As you know well, a Japanese scroll painting is a complex mounted object that is mounted from behind by multiple layers of backing. Whenever an artwork is conserved, it's typically remounted, which means that these layers need to be removed and eventually new ones applied. Although not visible from the front, therefore, the materials that constitute the backing for an artwork are absolutely crucial to their conservation. My research not only analyzes the physical and chemical properties of the backing papers and their adhesives, but also attempts to understand how they work together, forming a unique nexus of materials and methods in which the whole is greater than the sum of its parts. Let me explain by first introducing three components of the backing process. Aged paste or Furunori, used as a traditional adhesive for backing. And long fibered Japanese washi paper, like udagami and minogami, the actual backing layers, and the pounding brush or uchibake used to apply the adhesive. These components are key to the easy removal and reapplication of backing layers and the long-term preservation of a Japanese scroll painting. Furunori aged paste is a very specific material, even among traditional Japanese materials. Though many materials are recognized as traditional in Japan, counterparts can be found in other traditions for materials, such as animal glue, nikawa, and wheat starch paste, nori. On the other hand, Furunori is a Japanese particular material produced in conservation studios by storing fresh wheat starch paste for about a decade. New apprentices cook fresh paste to prepare furunori in the coldest week in January. After a decade, this furunori is then used in conservation by members of studio, including these same apprentices, who by then have matured into seasoned and independent conservators. Furunori is the industry standard as an adhesive for the backing of Japanese paintings. Conservators prefer it for its low adhesiveness in relation to fresh paste, thus enabling the peelability of backing layers for conservation, as well as its softness after drying. These characteristics have long been recognized, and it has been used for continuous in Japan. Furunori is mentioned, for example, in 17th century texts such as Gassen, Manual of Painting, and Honcho Shokkan, a culinary mirror of the realm. It has been used as an adhesive only to set backing paper for hanging scrolls and hand scrolls, primarily for its low tensile strength that is best for fragile, deteriorated Japanese paintings, and the high degree of retreatability that it enables. Because little was known about how the aging process affected the property of furunori, I conducted research to clarify its chemical composition and mechanisms involved in its generation. First furunori samples were collected from 9 traditional conservation studios. Their molecular weight and crystallinity were measured using the techniques of gel permeation chromatography, or GPC, and X-ray diffraction, or XRD. It's well known that gelatinized starch gradually recrystallizes when kept at a low temperature over the long term. It's also known that the recrystallized paste, otherwise known as the retrograded paste, loses its smoothness and increases its degree of repeatability after drying. The XRD results of all of the furunori samples that were tested revealed a recrystallized pattern. Oh, this one, this area, recrystallized pattern. And the XRD, which suggests that some furunori characteristics stem from the retrogradation caused by storage in a cool place for about a decade. On the other hand, GPC results showed that all furunori samples had lower molecular weights than fresh paste. This lower molecular weight appears to demonstrate that the texture softened after furunori application. Based upon these results, I attempted to generate furunori my own and assess the relation between its microorganisms and its molecular weight. We prepared furunori in small-scale jars and sampled the paste surface and certain intervals for GPC analysis and the examination of microorganisms. After 1 year, all samples achieved a peak molecular weight in the tens of thousands and appeared a peak molecular weight of 180 when the moles became the dominant microorganisms in the substance. with about after three months. This result suggests that molds, and especially the enzymes they generate, greatly impact the nature and production of Furunori. Glucose, a unit of starch polymer, has a molecular weight of 180. When mold assimilate starch, they generate enzymes called alpha amylase that decompose the starch into glucose and saccharide. In addition, some microorganisms also decompose saccharides into organic acids. Thus, all of Furunori samples had low pH values or high acidity. Based upon these results, I was able to summarize the process by which Furunori was generated as follows. The right figure, please see the right figure. First, fresh paste is stirred during the cold season. A part of the paste then undergoes retrogradation. That is to say, it recrystallizes due to storage at a low temperature and tends not to decompose due to low floating fungi numbers during the cold season. The retrograded part of the paste hardly assimilates microorganisms, so only the remaining portion of paste, this area, this left half area, parts of only the remaining portion of the paste, or the non-crystallized portion, is gradually decomposed by microorganisms into glucose and other saccharides, and finally into organic acids. This process begins at the top layer of the paste in the storage jar and then gradually works its way down to lower layers, taking approximately 10 years in all. Therefore, Furunori is characterized by a crystalline structure and low molecular weight and acidity. Conservators also report that Furunori tends not to grow mold. I believe this is so because most of the portion where mold might flourish has already decomposed. Thus, I was able to identify how the aging of waste paste influences its chemical properties and characteristics as an adhesive. Based on this deduction, we aim to prepare artificial Furunori, a polysaccharide similar to Furunori. We did so by initially storing it at a low temperature, like about 5 centigrade, and to form retrograded paste, and subsequently by mixing alpha amylase. The last stage involved washing the paste to remove intermediates with water containing organic acids. The resulting material showed very similar characteristics to Furunori, which supported our assumption. We were able to acquire a polysaccharide similar to Furunori within just a few weeks, thus drastically shortening the traditional aging process. These experiments with Furunori also resulted in new discoveries concerning its adhesiveness. We prepared samples washed with water that contained and did not contain organic acids. We did so in order to compare their adhesive force. If they were even, we would be able to prepare a new type of Furunori that was less acidic, because the high acidity of Furunori otherwise could be a potential problem for the long-term preservation of an artwork. What we discovered however, was that the samples washed in water with organic acids showed stronger adhesiveness than those without. The results suggested that adding organic acids exerts a positive effect on adhesive strength. This is because Furunori is always applied to backing paper that contain alkaline minerals. And thus, the organic acids increased hydrogen bonding. The acidity of Furunori thus positively affects adhesive strength, supporting Furunori adhesiveness, which otherwise demonstrates weak adhesiveness, enabling its repeatability. More comprehensive grasp of the adhesiveness of Furunori, however, requires an explanation of the role of the pounding or striking brush known as uchibake. Conservators make it a rule to use an uchibake to apply Furunori in order to understand better the role of the uchibake brush. We prepared samples with and without uchibake using 3 kinds of paper combination. One is wood pulp paper, upper one, and minogami, a type of washi or a long fiber paper that does not have that filler paper set, and a combination of Japanese paper known as udagami and misugami, both of which are washi that has mineral substance as filler. The last combination constitutes the set of papers that are actually used in conservation. We tested the adhesive force of the resulting samples in combination with Furunori and the use of the uchibake technique and brush. We found that the adhesive force increased in the samples with washi paper, that is to say sample 2 and 3, the latter half set, the latter 2 set, but that the adhesive force decreased in the samples with wood pulp paper, this one. These results imply that the effect of the uchibake method only when used on washi comprised of long fibers enhances adhesive strength. In turn, we can conclude from this that the combination of these 3 components, Furunori aged paste, the uchibake pounding brush, and long fiber traditional Japanese papers such as udagami and misugami, developed in tandem and mutually take advantage of their characteristics to achieve greater results in a manner that cannot be understood when each of these elements is examined in isolation. Finally, I'd like to introduce my research on the property of silk and how it relates to painting techniques. As is well known, silk is made from silkworm cocoons. Traditionally, in Japan, the silk thread extracted from these cocoons was reeled only by hand. During the 17th and 19th centuries Edo era, simple mechanical instruments were introduced to improve this method. And eventually, after the major revolution, during the latter half of the 19th century, an old reeling system was imported from the West. This change greatly improved the efficiency of silk production. But what has not been recognized until now is the degree to which this change affected the nature of silk fiber itself. The research in which I have been involved has shown evidence of this change. Scanning electron microscopes and thermal photos show cross-sections of each silk fiber. These photos show that when reeled by hand, light one, reeled by hand in the traditional manner, fibrin, a protein that is the chief constituent of silk fibers, is arranged loosely. When silk is reeled through the modern oat reeling process, however, the fibrin is tightly arranged due to strong twisting. In addition, the cross-sectional shapes of these fibers differ. The traditional type is flat and like elliptical, whereas the modern type is arranged in precise circles. This difference in silk fiber affects conservation practice. In traditional silk paintings, the painter often applied pigments to both the front and back side of the silk ground. This technique is no longer common among painters practicing traditional genres today. The reason has to do with the changing process of manufacturing fiber of painting silk. Yeah. Here you see digital microscopy photos of painting samples on silk showing malachite green pigment mixed with animal glue applied to both the recto and the verso sides of the silk by same painter. In the images you see here, the left one shows modern painting silk. The central one shows modern silk used for infill treatment. And the right one shows a traditional type of silk woven in the same structure as the central one. The surface of the sample using modern painting silk is filled with pigment, which can be attributed to the tightly woven structure of the cloth. This type of silk is woven too tightly to see pigment on the backside from the front, which is suggested one of the main reasons why pigment would be rarely applied from the backside in these days. I compare samples of modern infilled silk, that is to say, pieces of modern silk used to fill in traditional silk painting during conservation, with samples of traditional silk. Both showed gaps that allowed verso pigment to be seen and recto, which indicates that traditional painting silks had an effective textile structure for the showcasing of verso coloration techniques. Furthermore, I observed that pigment is applied on silk fiber more evenly in traditional silk, like this one. This suggests that fiber shape influences pigment fixability because traditional fiber has a flat surface. This difference explains why it's hard to match the color of infilled part to the original painting in conservation. And furthermore, why the infilled color seems to change when the viewer moves, owing to the different reflection angle between them. In addition, fiber shape appears to influence the transparency of each other because traditional fiber was thinner than modern fiber. This one, like this, like this. This might explain why verso coloring is more effective in traditional silk and perhaps why the technique is no longer prevalent today. Here, I have introduced the materials used in painting conservation field in Japan, all of which hold attractive characteristics and are used effectively based on scientific reasoning. I enjoy researching and clarifying them. It would be my pleasure if you feel excited about them and the results can be of some help for your work. Thank you.
Thank you very much, Dr. Hayakawa, for introducing us to your remarkable research. Among other things, I think it showcases why this substance, which seems so minor, old wheat starch paste or furunori, is so important in Japanese conservation. One of the most important materials. In my experience, you never bring up furunori with a conservator because they'll talk your ear off for hours about how their secret formula for making it in their own studio. But also your research shows, I think, the counterintuitive way in which it's the furunori and the washi and the uchibake technique that creates the conditions for effective backing in combination rather than individually, and the foolishness of trying to recreate this through only one component. And then I think with the research on painting silk, this idea that it's counterintuitively the hand reeling of silk and the traditional ways of spinning, extracting thread from a cocoon that create the most effective painting silks for all of the remarkable coloration techniques we associate with Japanese painting, polychrome painting. So thank you very much. I wanted to take this opportunity to field questions from the audience and also from our online Zoom community. Yes.
Thank you, Dr. Hayakawa. As you probably know, the work that you've done on aged wheat starch paste over the years has contributed enormously to the work that we do as conservators and mounters of Japanese paintings. In fact, it's probably not known to the audience, but this was an area that was really unexplored, probably starting 20, 25 years ago. And Dr. Hayakawa was able to sort of crack it wide open, enabling those of us who attempt to make aged paste outside of Japan under kind of funky natural conditions where we're aided by, microbes in the air. As we try to make paste outside of Japan, we are often guided by your research. As you know, myself and some colleagues have attempted to address these issues in occasional publications. And in doing the research, it seems to me there's an absolute lack of historic material or conversation or any kind of records speaking to aged paste. It's sort of this mysterious thing. And I know there are early mentions that maybe it was the work of Dani or small creatures, some kind of bug, this kind of fantasy. I'm curious, in your early research or even now, are there any early sources that in Japan that discuss this? I know it comes from China originally, but it just seems to be a hidden resource for so long. I wonder if you could speak to that.
最初に何か。ジェニファーよく知ってると思うんです。すいません、日本語で答えます。ダニに関してはジェニファーはご存知かなと思うんですけど、ダニが関係しているんではないかっていうような話を、30年ぐらい前に、ある農学部のプロフェッサーが教授が言っているんですけども、実際に私が関係したというか見たところによりますと、ダニの存在はむしろ、ある程度熟成が進んで 表面にカビが生えた後にそのカビを食べにダニが来ているだけであって、最初のファーストマテリアルとしてダニが必要ってことは全くなくて、ダニなしでも実際にはできるはずです。はい、
Jennifer, you probably know this well, but with regard to the theory about dani insects, dani, the English, I'm sorry, mites, thank you. With regard to the role of mites in the production of aged wheat starch paste, Furunori, 30 years ago, there was an agricultural science scholar who introduced this theory, but according to Dr. Hayakawa's research, it's probably after the mold appears in the aging process where the mites come in, but they're not actually essential to starting up the process of making the Furunori from the fresh paste. Are there any other questions from the, oh, yes, there's a question here. Oh, sorry.
Oh, here.
Yes,
Sandra, did you want?
I think she was first.
Thank you. Thank you for your presentation. I found it very interesting. I was wondering about the point where you said about how uchibake and the washi paper and the furunori are used, they kind of arose in conjunction with each other. I was wondering, when you were doing your testing, the types of paper samples that you used, the uragami and the misugami, like in Japan right now, paper suppliers and paper mills, there's a bit of flux in terms of how paper is being produced. So could you elaborate on when you said traditional Japanese paper? Like, for example, I know that if there's a shortage of Japanese kozo, they might import from Thailand or Laos or Paraguay. How these different kinds of fibers, would you expect to see the same results with differently sourced kozo?
私は繊維の専門ではないのでタイとかあっちの方で。すいません、私は紙の専門家ではないので、その辺はちょっと置いておきたいんですけど、紙を選ぶときに必要なのは、その種が楮であるかどうかっていうことももちろん重視していただきたいんですけど、その後どういう過程で出来上がってくるのか、どういう薬品を使い、あるいは伝統的にはアクを使うんですけども、どういうふうにそれを、処理してきているのかで、どのぐらい加熱するのかで、どういうふうに叩いて繊維をほぐすのかで全部影響してくるので、もし気にしていただけるのであれば、植物の種類が楮であるっていうこと以外に、その後の製紙の過程、製作工程にもご興味を持っていただければと思います。
Dr. Hayakawa mentioned that although she's not a specialist in Japanese paper as production, what's essential is, although mulberry koso paper, as you mentioned, is one of the main traditional forms of Japanese paper, not only is it the specific fiber type, but the process by which the paper is created that's going to lead to the characteristics that make it so effective in combination with Furunori and the uchibake brush technique. And so that is that involves everything from the ash that's introduced into the paper to the way the fibers are treated, the way it's beaten, and so forth. So it's really that process, its entirety, that's going to result in the special characteristics of the washi. So it's not necessary that the effectiveness of this entire nexus of the uchibake brush technique and furunori and washi is reliant upon a specific type of paper, but a paper that's made according to certain traditional principles.
Hello, Tanya Ueda, Museum of Fine Arts, Boston. Dr. Hayakawa, I enjoyed your presentation very much. Especially appreciated your research in silk fibers and the processing and the effect that has on painting silk, because it's on a personal level, as a Japanese paintings conservator, it helps assuage my the challenges that I have faced personally in painting infilled areas of treatments that I've done for infilling paintings on silk. It explains it explains that hardship quite nicely. But I guess I have two questions. One is your explanation that the development of processing the silk threads from hand reeling to sort of semi-mechanized reeling in the 17th and 19th centuries, and then to fully automated reeling resulted in the change in the shape of the threads. Likewise, through that time period, weaving technologies progressed to where in the late 17th and 18th centuries, painting silk is increasingly finer and more tightly woven. In spite of that, Edo period painters of especially Nikuhitsu ukiyo-e are known for their very creative use of urazaishiki, of that verso pigment placed on the back of the painting as well as the front. And so I'm curious to know if you think that the fact that that technique is not used much anymore, even in modern Nihonga, if that can be explained by the fully mechanized processing that now happens with silk threads, or if in addition, or if there's other processing methods that are done in addition to silk that help explain the difficulty and the sort of falling out of favor that urazaishiki technique that we've observed in modern painting practices. I don't know if that makes a lot of sense, but.
Tightly. ごめんなさい、すいません。私の表現が稚拙でして、タイトになったっていうのが多分2箇所出てきていると思うんですが、それは折り方がタイトリーになったっていうことと、あともう一つフィブロインがすごくタイトリーになったっていう2つの意味で言っていて、多分その両方がきちっとあったので、目が詰まってしまったので、裏材式の効果がなくなったと考えています。はい。
It may have been confusing because she used the word tight in two senses, but that does include both the winding of the fibers in the silk and also the actual weaving of the silk itself, which becomes tighter. So that tighter mesh in the silk is certainly a reason why the verso coloration urazaishiki becomes less effective over time. So it's not actually purely the thread, the hand reeling itself, the loss of hand reeling itself, excuse me. I'm sorry, there's a second question.
Thank you for mentioning so many things that are of interest to people and don't have many chances to hear about them. There's a couple of things I'd like to mention, however. One cannot discount the fact that the technique of the brushwork overall and the skill of the person using the brushes is of extreme importance. It isn't just the materials here that unfortunately affect the whole outcome of the restoration or conservation as it is. And I think in these kinds of measurements, we don't have a chance to really evaluate that very well. Another point I'd like to mention is that it's very important, of course, the uchibake, but also the brushes that are used for the smoothing all and the adherence of the adhesives and so on is extremely important in the outcome of the adhesive qualities. We tend not to think about that quite as much possibly. One more thing that there's a problem now for some mounters, or some more than there was in the past, of the use of kiln-dried paper. So many mountings these days, which would primarily have been done with former techniques, are now using kiln-dried paper, and that reacts extremely differently than traditional papers in terms of longevity and various other qualities. And one more small point, sorry to mention, but I think one thing that's being overlooked here in terms of the use of uranugu, or pigment on the reverse, is that in the past, all of the silk was basically was beaten. And so it was therefore much easier to apply the pigment to the reverse. And I think that is the primary reason why that has fallen into less use, because there is no one out there hardly who can still do the beating of the silk. And that made it much more absorbent to the pigments. Anybody else?
Thank you very much for your comments. Okay, I think we are just about out of time here, 2:40, so we'll need to proceed to the next presentation. But please join me in thanking Dr. Hayakawa.